Hello, everybody. Happy almost Thanksgiving. Hope you all are doing okay. We're going to finish up talking a little bit about some organic chemistry before we head out for the Thanksgiving break. So last time, if you recall, we looked at some alkanes, some isomers, cycloalkanes, reviewed some of those line structures and how to draw those things. Today, we're going to move to the next part, which is looking at functional groups and reactions. So far we've looked at the structures, and everything we've drawn has really been carbon-based, carbon-hydrogen. But one thing about these molecules, like the ones that are shown up here, is they're really not reactive. You can burn them, they're fuels, but that's about it. There are some things that you can react them with, but generally you can't react them with other stuff. And one of the great powers of organic chemistry is that the reactions are really predictable. If you have this type of molecule, you can put this type and you can actually hook it on exactly where you want to, pretty much. And that's why organic chemistry has become so powerful and so important in things like drug design and other types of building small molecules. Because you really can, whatever kind of molecule you want to draw, you want to make, you can set up an organic reaction scheme, like a set of reactions, to make that thing. And then you can go in the lab and actually do it. So in order for that to work, we need reactive sites. We need parts of the molecule that can react in predictable ways. And that's what we call functional groups. Functional groups are the parts of the molecules that can do the reactions, that are reactive in a predictable way. And so what we're going to do is we're going to draw some of the different functional groups, make ourselves a little chart with some examples, and then how to pick these things out. All right. So we'll start with what is actually not really a functional group, but a name of a category. And I guess maybe you could technically think of it as a functional group, which is what we've already talked about, the alkanes. So just carbon and hydrogen, and carbon single bonds. And that's all the stuff we've been drawing, right? Like this kind of stuff. And then cycloalkanes would fit in that group as well. So those are the alkanes. And it's not really a functional group, so we'll kind of just leave that off the table. And let's make a table where we have a name. And then we'll have a general structure. Like, what are we looking for in general? And then we'll give an example of an actual structure that has this particular functionality. So our first one is going to be very similar to the alkanes, and it's the alkyl halides. Alkyl means kind of like alkane, so it comes from an alkane. And halides are the halogens, so that's fluorine, chlorine, bromine, and iodine. So a general structure of an alkyl halide would have a carbon that is connected to some halogen, and then some other stuff connected on the other side. It could be whatever. But X here could be fluorine, chlorine, bromine, or iodine. And so an example structure there would be something like, if we just drew an alkane and then put a chlorine atom on there. So, we added an alkyl halide. Now you could have multiple ones. You could have bigger structures. We could have rings. So we could start with a cycloalkane like this and put a Cl here and a bromine down here or whatever. These are all examples of alkyl halides. They're an alkane that also has these halogen atoms on it. And just having that is a source of reactivity. So now when these things undergo reactions, that carbon that has that halide coming off is where that reaction is going to happen. And if you go on and take organic chemistry, you'll see lots more examples of that and how to actually use it. We're going to focus on a few different reactions that are not these right now. So you just have to know how to identify these different types of functional groups. All right. So after alkyl halides, we have, and we're going to do these together, alkenes and alkynes. So very similar words here, alkane, alkene, alkyne. So that can be a little bit tricky to keep straight. But alkanes we already talked about. Alkenes are double bonds. And alkynes are triple bonds. So some examples of alkenes in a line structure, they can be straight chain like this. They can have multiple alkenes. You can have multiple double bonds. They could be in a ring. Let's do a 5-membered ring with a double bond on it and some other carbon coming off this way. So, all kinds of different possibilities just with a double bond. And then alkynes, we've got a triple bond. The only thing to note here is if we look at each of these carbons and we think back to the molecular geometry stuff, you'll notice that each carbon only has 2 groups attached to it when we talked about electron groups. And so that means that this is going to have a linear geometry. So when we draw line structures with alkynes, we don't zigzag them like this. They're actually straight. So an alkyne might look like that. And the carbons here, if we number them, would be 1, 2, and then we've got a carbon on one side of the triple bond, a carbon on the other side, and then 5 and 6. So you can see the linear triple bond there. Now I drew the lines different lengths. That's not correct. Those should all be the same length. That was just me being messy. It's a little hard to draw these things on the computer sometimes. Okay, let's get the idea. All right, so we've got alkyl halides, alkenes, and alkynes. Let's continue. And I would recommend that you write these along with me so that you get some practice with how to draw these things. Okay, next we're going to look at some other functional groups that involve other atoms attached to carbon, specifically O and S. So we've got alcohols. An alcohol is a carbon with an OH, other stuff attached. So again, we can draw whatever we want with OH on there. You can also have multiple alcohols, diols, triols, put them around wherever. That's called an alcohol, OH. Good hydrogen bonding there, high boiling points. We're going to see lots of those when we get into the biological molecules next week and start talking about carbohydrates and lipids and proteins. All right, similar to an alcohol is a thiol, which is with sulfur instead of oxygen. So same kind of thing. But this time SH instead of CH. And thiols smell really bad. So a lot of bad smells that we know of come from thiols. Some come from amines as well. But a lot of those like sulfury kind of fart smells are thiol based. Okay, and then we have ether. And ether is another oxygen-based functional group that has a carbon on either side of the oxygen. So rather than an OH, now we've got the oxygen in between 2 carbons. So some examples here, a couple of different ways we could do this. So we could have like a chain and then an oxygen and then more carbons. That's an example of an ether. You can also have the oxygen inside of a ring. So you can do something like that. Again, it still fits that definition. Oxygen with a carbon on either side. So that's an ether. This would be called a cyclic ether, just like a cycloalkene. All right, so those are some of those basic functional groups. And then there's another set of them that are all based on the same kind of functionality. And so we're going to group them together. And these are going to be the carbonyl functional groups. Now, a carbonyl is a carbon double bonded to oxygen. And this is an extremely important type of functionality that we're going to see when we look at reactions. We're also going to use this type of functionality when we look at all kinds of biological molecules, whether it's carbohydrates, lipids, proteins, all of those, nucleic acids. All of these are going to have carbonyl functionality like this. So these are sometimes the hardest ones to keep straight because they all seem really similar. So we're going to kind of start from the simplest ones and then build up from there. And then another thing that you need to know as we do these is that when we write a capital R, it just means some organic molecule. So some stuff that involves carbon, hydrogen, maybe other stuff. But it's we can assume it's based on carbon, and then it's got whatever else. So it's sort of like up here, we drew these little just lines saying whatever is out there. But sometimes we want to be more specific. We write R to say that there's some organic stuff here, but it could be whatever. It could be anything. All right. So let me show you what that looks like. So again, we've got our functional group name, our general structure, and our example. Our first one is called an aldehyde. Aldehyde is going to have a general structure of the carbonyl, C double bond to oxygen. And then coming off that carbon is a hydrogen on one side. And on the other side of the carbon coming off is that R group. So just kind of generic stuff. Oops, not writing. There it goes. So that could be, CH2 or CH3. It could be CH2, CH3. It could be a big ring. It could be some giant molecule, whatever. So an example of that in a line structure, if we were to draw something like this, we have to be really careful here. We have to write this H here because remember what a line structure means. If we leave that H off, then we're assuming that that's a carbon right there. And that's not a carbon right there. That's a different functional group. We need to make sure there's a hydrogen there. So we can put it there, or we can actually leave it off because line structures, we tend to leave off the hydrogen. So we could also draw this, we could also draw this like this and just not have any line there. But if we put a line, we've got to put the hydrogen because otherwise we're going to assume it's a carbon, and that's not an aldehyde. So aldehydes are also have some interesting smells. Some good, some bad. Many people are familiar with formaldehyde, which is where you have an H on both sides, that kind of like preservative, stinky thing. And that's aldehydes. Okay. So similar to aldehydes are ketones. Ketones are also based on a carbonyl, but instead of having a hydrogen on one side, they have a carbon on both sides. So we're going to go R and R prime or R whatever, just saying that these don't have to be the same on both sides, but there's carbon stuff on both sides. So here is where we are, we can draw things like this because we know that this means that there is a carbon on this side and a carbon over here. So two carbons there. This molecule is acetone, which is an important solvent used in nail polish remover and other things. Because there's carbons on both sides, you can also have cyclic ketones. So you can have things like this. Certain types of carbohydrates are ketones. So things like fructose is a ketone. Ketones are also really important in steroids and hormones, which are in the lipids class of molecules. So we'll see lots of those as well. Just trying to keep them straight. Think about whether or not there's a hydrogen there. All right, so next we have the carboxylic acid. This is going to be the source of acidity for organic molecules, organic acids. This time we've got the carbonyl. Notice that's in all of these. And an R on one side, and then an OH on the other side. And this H is very acidic, which means that it can come off easily. Remember that the definition from the last chapter, if a molecule can donate a hydrogen, that makes it an acid. And so this H connected to the O is easy for this molecule to donate energetically, so it often gets rid of that. So drawing those, we have something like this, which is acetic acid. A 5% acetic acid solution is vinegar. You can also have, of course, bigger molecules with these acids. When we look at amino acids, those are all going to have these functionality on them. That's where that acid comes from in amino acid, is that there's a carboxylic acid functionality. All right, again, similar to carboxylic acid, we have esters. Esters start the same as carboxylic acids, but this time they have O with more carbon on the other side of the O. Esters are often confused with ethers because those words are so similar. So ether, the O is in between two carbons. Ester, it's got that carbonyl. So you try to keep those straight. Flashcards are a good thing for this because really you do just have to memorize what's the name and then what's the kind of a structure that goes with that name. Those of you who are taking anatomy or if you've taken that kind of thing, you know how this works, where you've just got a whole big list of stuff and you just got to know what they all are. All right, so for some ester examples, we can start with a cyclohexane and then an O and then, some other carbon stuff coming off the other side. Could be whatever. But the idea is here you've got not just a carbonyl, and this is not an ether, not an ether. This whole thing together is an ester functional group. Okay. Then we've got our last carbonyl functional group, an amide, or sometimes called an amide. Similar to an ester, but with nitrogen instead. And I'm just going to leave these things blank because they can either be carbon or hydrogen. So an amide might be something like, let's look at a similar structure. So we'll start with this ring, put in the carbonyl, and then it could be just NH2 over there next to the carbonyl. We could also have carbon stuff coming off of there. These amide functionalities are also sometimes called peptide when they're involved in a protein, because this is how amino acids link together to make proteins. And we'll get into that a little bit more in that chapter. All right, and then our last functional group, it's not a carbonyl. It's amine. It's similar to amide with that am, but when we have the N instead of the D there, we're talking about not having the carbonyl functionality. So an amine is going to have R and then N with whatever coming off of it, rather than the carbonyl in the middle. So we might have something like this. We might have it coming off of somewhere else with other carbon stuff coming off of it. So again, there's infinite possibilities of how you can set these things up, but the goal is to both be able to draw an example of these functional groups, but also to be able to recognize an example. So if I drew a molecule for you, could you pick out what functional group is in that molecule? Okay. And next we're going to look at these terms: primary, secondary, and tertiary. They correspond to how many carbons are attached to something. Primary is also sometimes labeled as a 1 with a little circle, secondary 2, and tertiary 3. So if you had 1 carbon attached to something, you might call that primary, 2 carbons secondary, 3 carbons tertiary. So let's see how that works with some of those functional groups that we just talked about. So if we had a, let's look at 3 different alcohols here. They're each butyl alcohols. They're butane, so 4 carbons with an OH. So they are isomers of each other. All right, and so we're going to be looking at the carbon that that functional group is connected to, right there. So if we look at the carbon that the functional group is connected to, we want to ask how many other carbons is that one connected to? So we can see here this carbon that has the OH coming off of it has 1 other carbon connected to it. This one has 2 carbons connected to it. And then this one has 3 carbons connected to it. So we would call this a primary alcohol. We would call this one a secondary alcohol. And we would call this one a tertiary alcohol. And that's going to affect its reactivity and what kinds of things it can do. When we look at some of the biological molecules next, this is kind of all preparation for that. We're going to say, okay, is this a primary site or a secondary or a tertiary alcohol or amine? With amines, it's a little bit different because amines can have multiple carbons connected to them without changing the functional group. So what I mean by that is if we added another carbon onto the oxygen here, we wouldn't have an alcohol anymore. We'd have an ether. So we can't do that. We're always looking at the carbon that the OH is coming off of when we're trying to designate it as primary, secondary, or tertiary. But with amines, it's a little bit different. So here's our primary amine. A secondary amine actually has 2 carbons coming directly off of the nitrogen. And a tertiary amine has 3 carbons coming off of the nitrogen. And I just drew like one, just a CH3 coming off here, but it could be it could be some bigger chain or a ring or whatever. So with the amines, we're looking at the nitrogen itself, not the carbon next to it. And we're saying how many carbons are connected to that nitrogen. So in this case, it's 1. In this case, it's 2. And in this case, it's 3. So this would be our primary amine, our secondary amine, and our tertiary amine. All right. Let me check Discord, make sure nobody's any questions here that I'm missing. All right, the very last part that we're going to look at is hydrolysis and condensation. So 2 different actual reactions. So we've only really looked at the structures, these different organic structures, and how to think about them in different ways. We haven't looked at how they actually react to each other. And it's a huge, huge field, right? You could take an entire class on organic chemistry, 2 semesters even. You could study it for your whole life and still not know all the ways that these molecules can react with each other. So we just have to pick a couple important ones. Because we're going into the talking about biological molecules, we're going to focus on a couple of the reactions that are really important for things like carbohydrates, lipids, and proteins, and nucleic acids, because that's what we're going to be focusing on for the last 2 weeks of the class. So let's take a look at just two reactions. The first one we're going to look at is called hydrolysis. Hydrolysis, that word is made up of 2 words, hydro, which means water, and then lysis, which means to break or to cut. So this is molecules being split up by the addition to water, or by the addition of water. So add water, H2O, and split. And then the second one is actually the opposite, and it has two names. It's more commonly called condensation, so like condensing. So hydrolysis was splitting apart, condensing is bringing together. But we also sometimes call it dehydration because it involves the loss of water instead of the gain of water. So in a condensation reaction, we're going to remove water and connect two molecules. Now, there's lots of different ways that we can do this. Both of these reactions are kind of general categories. We're going to focus on a couple examples in particular. So let's start with hydrolysis. And we're specifically going to look at hydrolysis of an ester or amide. So if you go back up to review a little bit, you'll see that an ester has a carbonyl group and then an oxygen and then more carbon. We are going to use one particular ester here. So just to see this example, I'm going to actually write it out as a condensed structure so we can see what all of the atoms are doing. And I'm going to color code it a little bit. So my apologies if you can't see these colors. Hopefully you can still follow along, but I'm going to put this part in green. So there's our ester, right? Carbon double bond oxygen, another oxygen, and then carbon. And then this also has this carbon over there. So when we hydrolyze it, hydrolysis, we are cutting the molecule in two and adding water. What does that mean? Well, esters and amides are always going to cut in the same way. They're always going to cut right next to the carbon, in between the carbon and the oxygen, or the carbon and the nitrogen. So this bond right here is getting cut. And if we just simply redraw what we've got, if we just cut that, what we would have is on the left side, CH3, C double bond O. And then on the right side, OCH3. Now, if you look at these two molecules that are now not connected anymore, you should see some problems. This carbon only has 3 bonds, and this oxygen only has 1 bond. Usually we want oxygen with 2 bonds. And so this is what happens when we add water, is the water also splits up, and the OH goes on one side, or part of the OH goes on one side, and the other H goes with the other oxygen. So now we have 2 molecules. We have CH3OH, which is an alcohol, and we have this, which is a carboxylic acid, acetic acid. I'm going to separate these a little bit so you can see it better. So we have 1 molecule on the left. We add water, we break it in 2, and then part of the water, the OH, goes on the left with the carbon, and then the other H goes over here with the oxygen. The same thing can happen with an amide. So let's take a look at that. We're going to use a very similar structure. And this time, instead of having an ester part, we're going to have an amide part. And we could have carbons coming off of here too, but we're just going to leave it with the NH2. So we're going to do the same thing. We're going to react this with water, which tells us it's hydrolysis. And we're going to break that bond in between the carbon and the nitrogen. Then with our new molecules, we've got this and NH2. So the H and the OH from the water are going to do the same thing here. So we're once again going to make acetic acid. And then the other H is going to attach to the nitrogen. So we're going to have NH3, which is ammonia in this case. So that's hydrolysis. Now, this reaction is important in many parts of biochemistry. For example, when fats break down into glycerol and fatty acids, those are hydrolysis reactions just like this. Fats are esters, as we'll see. When proteins are broken down into amino acids, that's the hydrolysis of these peptides in a similar way. Now, we should note, we're not going to get too into it in this class, but if you go on and learn more about this, just plain water doesn't really do this. You actually need some acid or base to catalyze this. But functionally, the water is the thing that is reacting, so we're just going to leave it like that. All right, so condensation then, the other part of this, is going to be the opposite reaction. So we're going to take an acid and either an amine or an alcohol. We're going to put them together, take water out, and then have one molecule together. So I'm actually going to use the exact same example so that you can see how it works the same way. So here's my acetic acid. And to that acetic acid, I'm going to add some methanol, which is CH3 with an OH there. And I drew it kind of backwards so that the two OHs can be together, but normally we would just draw this CH3OH, but same idea. All right, so in a condensation reaction, we're going to take water out. So we're going to take H2O and remove them. So that would be the OH here and the H here. So H2O is leaving and becoming water. And the result then is that these two molecules have to connect together like that. Again, if you go on and take organic chemistry, you'll learn all the mechanisms by which this happens and how to figure out all kinds of different molecules and what they're going to do. But for our purposes, we just want to know if I have these two molecules and I know it's a condensation reaction, what am I going to get as a product? And what I'm going to get is this ester. So the byproduct here is water. We remove water, connect what's left, and we have this. And then similarly, we can do that with an amide as well. This time, I'm going to do it just with a line structure because we haven't really looked at that yet. Let's look at a little bit different, bigger molecule just to show that we can do that as well. So let's start with this big carboxylic acid. And let's add to it a much bigger amine. Let's do like a cyclopentyl amine. Right? So we've got cyclohexyl over here, cyclopentyl over here. But the idea is the same and the reaction is the same. So don't be scared if the molecules get bigger and bigger. This is the thing about organic chemistry. It's just the functional groups that are doing the thing. Whatever else stuff is going on in the rest of the molecule, you don't really have to worry about right now. So it doesn't matter what kind of big stuff. And when we get into the biological molecules, they're big. You know, these are big molecules. But that doesn't affect what's going on with the functional groups. The functional groups are still doing their functional group thing. So we're going to get rid of OH. We're going to get rid of one of the two hydrogens. Remember, there's two here, so let's not get rid of both of them. In fact, just to make that super clear, let me redraw that. So we're taking one hydrogen, but we're not taking the other hydrogen that's connected to the nitrogen there. Okay. And then we're combining those. And so when you draw the product, remember, you're not messing with the rest of the molecule. So just leave the rest of the molecule alone, draw it just as is, and only change the functional group, the thing that's actually changing. So we're going to keep our cyclohexane over here. We've got our carbonyl right here. And then here's where the change comes now. We've got the OH and H leaving as water. And so this carbon from the carbonyl is now directly connected to the nitrogen. And that nitrogen still has one hydrogen connected to it. And it also still has this cyclopentyl group connected to it. I'm changing the angle a little bit just because to maintain the zigzag. but I could keep it pointing down too. That doesn't matter. Remember, there's free rotation around these single bonds. So that would be my condensation product plus some water after we've combined those like that. All right. So we've got hydrolysis, we've got condensation. We will see this more in the next chapters as we get into the biological molecules. These are how those things connect also. So we'll see hydrolysis and condensation of sugars. We'll see hydrolysis and condensation of amino acids, of fatty acids and glycerol, and all kinds of interesting biological molecules. So until then, have a great Thanksgiving. Stay safe. Take care of yourselves. Take care of each other. And I will see you next week. Bye, everybody.